Hello and welcome everyone. Thank you for joining us for our expert sessions. These short webinars take place every week and last no more than 30 minutes, bringing you valuable insights from industry experts. Today's session will be presented by Sunny Solanki. He's a senior technical manager at I-Gard. Sunny is an electrical engineer from McMaster University with 8 years of experience in protection systems and relays. Throughout his career, he has educated consultants and end users on the benefits of integrating electrical protection products into their designs to enhance personal and equipment safety. He specializes in providing commercial and technical support for various projects and applications, including HRG systems, energy systems, hybrid HRG systems, ground fault and arc flash protection systems, and personal protection products. We are excited to have him here today, and we appreciate your participation. Without further delay, I would now request Sunny to take over from here.
Thank you, Devansh. Today's presentation is on frame voltage protection and compliance with CEC, NEC, and mining standards codes. So to start off with, frame touch voltage. Frame touch voltage protection is a critical safety feature that prevents electrical shocks by ensuring that metal frames and enclosures of electrical equipment remain safe to touch even during electrical faults. So it's important to do this to reduce the risk of electric shock in high-risk environments, protect personnel working near energized equipment, and enhance workplace safety by addressing potential fault conditions. So according to IEEE 80, touch potential is defined as the potential difference between ground potential rise and the surface potential at the point where a person is standing while at the same time having a hand in contact with a grounded structure. So what causes touch voltage? So during a fault, let's say if we have a fault here, current flows into the ground and seeks a return path to the source, which would be the substation here. This raises the Earth's surface potential near the fault location, creating a ground potential rise. If a person touches the mobile equipment here, connected to the ground, the elevated voltage can transfer, causing a shock risk. So it happens when fault current flows through the equipment's frame, right here, fault B, and this raises the frame's voltage relative to the ground. It creates a hazard for personnel in contact with the equipment while standing on the ground. So in the M421 standard, it requires you to limit the transfer of potential to 100 volts or less to movable or mobile equipment. It has to be limited to 1 second or less, and the system should prevent this transfer of potential. When the transferred potentials are influenced by the resistance of the ground electrodes, the electrodes shall be measured after installation or modification to ensure that the transferred potentials do not exceed 100 volts between ground points. So they would just test the grounding electrodes to see what the difference in resistance is between the ground points and determine if there's a potential to be transferred that can exceed 100 volts. So you can use the split factor to take into consideration the calculation of ground potential rise. In the National Electrical Code, it says that systems supplying portable and mobile equipment over 1,000 volts shall comply with A through F. So for portable or mobile equipment over 1,000 volts, it shall be supplied from a system that is high resistance grounded or grounded through an impedance. And if your system is delta connected, you have to establish an artificial neutral using a zigzag transformer. Exposed non-current carrying metal parts of portable or mobile equipment shall be connected to an equipment grounding conductor to the point at which the system neutral impedance is grounded. and the voltage developed between the portable and mobile equipment frame and ground by the flow of maximum ground fault current shall not exceed 100 volts. In terms of ground fault detection and relaying, ground fault detection and relaying shall be provided to automatically de-energize any component of a system over 1,000 volts that has developed a ground fault, and the continuity of the equipment grounding conductor will be monitored to automatically de-energize the circuit of the system over 1,000 volts upon loss of continuity of the equipment ground conductor. In terms of isolation, the grounding electrode to which the portable or mobile equipment system neutral impedance is connected, it shall be isolated from and separated in the ground by at least 6 meters from any other system or equipment grounding electrode, and there shall be no direct connection between the grounding electrodes, such as buried pipe and fence, and so forth. For trailing cable, it has to meet the requirements of Part 3 of Article 400 for cables and 490.55 for couplers. Now, I-Gard's solution is a combination of a ground fault ground check relay or ground monitor relay, and the GCHK 100 protects against frame voltage as well. So it has 3 functions. It can pick up ground fault, it can pick up open circuit and short circuits along trailing cables ground connection, and it can also pick up frame voltage between 40 to 100 volts. So the response time is within 100 milliseconds for standard detection and 30 milliseconds for voltages greater than 100 volts AC. As I mentioned, it identifies ground loop short and open conditions and internal leakages with respect to ground fault. And it prevents electrical shock risk from ground connection failures or equipment faults. We have adjustable ranges between 40, 60, 80, and 100, going up in 20-volt increments starting at 40. These are adjustable based on the dip switch settings at the front of the relay, and the relay also has normal and fail-safe capabilities, as well as ground fault pickup levels. I think it's between 0.5 amp to 12.5 amps. So the case study of the use case for the GCHK 100 relay comes from a mine in Peru, which was facing issues with electrical shock at their mobile equipment, and they wanted to improve their detection method for frame voltage protection and control to increase safety and reliability for their workers. They also wanted to comply with CSA and NEC. So they installed the I-Gard's GCHK 100 for fast fault detection and frame voltage detection, as well as open short of the ground check connection. It ensured compliance with CSA M421 and NEC 250. In doing this update, fault detection improved significantly, shock risks were reduced, and system reliability increased. And the conclusion was it enhanced safety for personnel. We achieved compliance with code regulations, and it was a cost-effective solution with reduced operational disruptions. That is all for today's expert session. Feel free to reach out if you have any questions. As of right now, we'll be going through them. It doesn't look like we have any questions, so feel free to tune in on our next session, which will be happening next Tuesday. And I thank you all for your attendance today. Thank you.